Look up at the night sky. What do you see? Twinkling stars, distant planets, maybe the faint glow of the Milky Way. But hidden within that vast darkness lies something far more mysterious, something invisible to our eyes, yet bursting with unimaginable power. Gamma rays, the most energetic form of light in the universe, are streaming through space, carrying secrets from the most violent and extreme events in existence. These aren't just random flickers, they're cosmic fingerprints, clues to phenomena we're only beginning to understand. And the most baffling part, nearly half of the gamma rays flooding the cosmos come from unknown sources. That's right, despite decades of research, the origins of much of this high-energy radiation remain a profound mystery. This is the enigma of the cosmic gamma-ray background, a diffuse glow that blankets the universe, whispering tales of supermassive black holes, colliding neutron stars, and perhaps even dark matter itself. Gamma-ray astronomy isn't just about studying light. It's about decoding the universe's most violent dramas, events so powerful they can warp space-time and unleash energies beyond human comprehension. Every burst, every flicker is a piece of a puzzle that spans billions of light years. And yet, the harder we look, the more questions we uncover. Why do some regions of the sky glow brighter than others? What invisible forces are accelerating particles to near light speeds? Could some of these signals be evidence of physics beyond our current understanding? That's where our journey begins. Over the course of this exploration, we'll unravel 25 of the most compelling mysteries tied to the cosmic gamma-ray background, from baffling blazars to strange excesses in the data that defy explanation. Each discovery peels back another layer of the cosmos, revealing just how much we still don't know. So if you've ever wondered what lurks in the shadows of the universe, or how scientists are piecing together the story of these high-energy enigmas, you're in the right place. Strap in, we're about to dive into the invisible fireworks of the cosmos, where every clue has the potential to rewrite what we thought we knew about space itself. The first mystery on our list might sound simple at first glance. Why does the entire sky glow with gamma rays? But peel back the layers and you'll find a cosmic riddle that's kept astrophysicists awake for decades. Imagine turning off every known gamma-ray source, black holes, pulsars, supernova, and yet the universe still hums with this faint, persistent light. That's the diffuse gamma-ray background, an eerie uniformity stretching across the cosmos like static on an old television screen. So where does it come from? One leading theory points to unresolved point sources, millions of distant objects like active galaxies or neutron stars too faint to detect individually, blending together into a cosmic fog. Think of it like standing in a dense forest at night. You might not see each firefly, but their combined glow lights up the trees. Yet when scientists tally up known gamma-ray emitters, there's a gap, a mismatch between what we've catalogued and the total radiation we observe. Then there's the dark matter angle. If this elusive substance is made of particles that annihilate upon collision, as some models suggest, those crashes could release gamma rays. It's a tantalizing idea. The glow we see might literally be the universe's shadowy skeleton revealing itself. But here's the catch: no one's found definitive proof. The signal lacks the telltale bumps or patterns that would nail dark matter as the culprit. And let's not forget primordial black holes, hypothetical relics from the Big Bang. Could countless tiny black holes, smaller than atoms, be evaporating across space, leaking gamma rays as they fade? It's a wild card, but in a puzzle this complex, even fringe ideas deserve a seat at the table. What makes this mystery so stubborn is its sheer scale. Unlike localized gamma-ray bursts, this background is everywhere, meaning its source or sources must be equally widespread. It's like trying to solve a global whodunit where every suspect wears the same mask. Every time a new telescope launches, scientists hope for a breakthrough, but the answers remain just out of reach, wrapped in the universe's oldest habit, refusing to give up its secrets easily. Now shift your gaze from that mysterious cosmic fog to something far closer to home, an unmistakable pair of massive gamma-ray structures towering above and below our own Milky Way. Meet the Fermi Bubbles, two colossal lobes stretching 25,000 light-years each, like a cosmic hourglass rooted deep in our galaxy's heart. Discovered just over a decade ago by NASA, a Fermi Gamma-Ray Space Telescope, these bubbles glow with high-energy light, yet their origins remain one of the most heated debates in modern astrophysics. Picture the scene. Our galaxy's supermassive black hole, Sagittarius, a star, sits quietly today, but what if it wasn't always so calm? One leading theory suggests these bubbles are remnants of a colossal eruption, a time when the black hole devoured a huge amount of matter and burped out twin jets of energy millions of years ago. The sheer scale of such an event is staggering. Imagine a detonation so powerful it punched gamma rays halfway across the galaxy, leaving behind these immense ghostly remnants. Yet not everyone's convinced. Some researchers argue the bubbles could be fossils of a starburst frenzy, a period when the Galactic Center birthed stars at a breakneck pace. Massive stars live fast and die violently, exploding as supernovae whose combined shockwaves might have inflated these structures. There's even evidence of past star formation near the Milky Way's core that could support this idea. Here's where it gets stranger. The bubble's edges are unusually sharp, as if carved by some unseen force, and their gamma-ray emissions don't quite match predictions for either black hole outbursts or starburst activity. Some speculate dark matter interactions or exotic particle physics could be at play, though these ideas linger on the fringe. What's undeniable is how these silent giants challenge our understanding of galactic evolution. Whether relics of a black hole's tantrum or the aftermath of a stellar baby boom, the Fermi Bubbles force us to confront a simple truth. Even our home galaxy hides violent chapters we're only beginning to read. Every new observation peels back another layer, revealing just how dynamic and unpredictable the cosmos can be. Gamma-ray bursts are the universe's most explosive enigmas, cosmic detonations so powerful they outshine entire galaxies in seconds. These fleeting flashes of gamma rays pack more energy than our sun will emit in its entire lifetime, yet their origins remained a total mystery until just a few decades ago. Now we know these bursts come in two distinct flavors, each tied to some of the most catastrophic events in existence. The short bursts, lasting less than 2 seconds, are thought to be the death cries of colliding neutron stars. Picture two city-sized objects, each so dense a teaspoon of their material weighs 1 billion tons, spiraling toward each other in a gravitational dance. When they finally collide, the impact creates ripples in space-time gravitational waves and unleashes a fireball of gamma radiation. But here's the twist: not all short bursts fit neatly into this box. Some lack the expected afterglow or come from regions devoid of neutron star pairs, leaving scientists scrambling for alternative explanations. Could some be the work of black holes tearing apart wandering stars, or perhaps signatures of exotic, undiscovered physics? Then there are the long bursts stretching from seconds to minutes, born from the collapse of massive stars in supernova on steroids. As a star dozens of times heavier than our sun exhausts its fuel, its core implodes, forming a black hole. But instead of a quiet fade, the dying star launches jets of material at nearly the speed of light, punching through the stellar corpse and beaming gamma rays across the cosmos. Yet even here, outliers defy expectations. Some long bursts originate in galaxies with surprisingly low star formation rates, while others flicker in patterns that don't match current models. The real head-scratcher: a handful of bursts straddle the line between long and short, blurring the classification entirely. These misfits might hint at entirely new progenitor scenarios, like white dwarfs colliding with neutron stars or even the ignition of primordial black holes. Each unanswered question underscores how much we still don't understand about these titanic explosions. Every new detection peels back another layer, revealing a universe far more unpredictable and far more violent than we ever imagined. It seems like an obvious pairing supernova, the explosive deaths of stars, should naturally lead to gamma-ray bursts, the most luminous flashes in the universe. Yet nature loves to defy expectations. Only a tiny fraction of collapsing stars, roughly 1 in 10,000, produce these spectacular gamma-ray fireworks. So what separates the cosmic heavyweights that unleash GRBs from the vast majority that fade without such fanfare? The answer lies in a delicate interplay of physics, where a star's final moments hinge on factors as subtle as its spin and as fundamental as its composition. Take jet formation. The star's last gasp has to be perfectly asymmetric. For a gamma-ray burst to occur, the collapsing core must channel its energy into ultra-fast, narrow jets punching through the stellar debris. If the explosion is too messy or spread out, the energy dissipates, leaving behind a normal supernova. Picture trying to force water through a garden hose versus letting it spill from a bucket. Only the focused jet reaches the distances needed to create that unmistakable gamma-ray signature. But even that's not enough. The star's rotation plays a starring role, acting like an engine winding up those jets. Too slow, and the collapse lacks the spin needed to focus the blast. Too fast, and the star might tear itself apart before the crucial moment. Then there's metallicity, an odd term astronomers use for elements heavier than hydrogen and helium. Stars born in metal-rich environments like our Sun tend to lose their outer layers through stellar winds long before death, robbing them of the dense fuel needed to power GRBs. In contrast, metal-poor stars, more common in the early universe, retain their mass, creating the ideal conditions for a gamma-ray spectacle. It's no coincidence that the most distant GRBs often hail from galaxies with compositions resembling the pristine cosmos of billions of years ago. But the plot thickens when we examine the outliers. Some supernovas show faint gamma-ray emission, not quite bursts, but whispers of a process that almost succeeded. Others, like the infamous supernova 2558A, had all the ingredients for a GRB: rapid rotation, low metallicity, and yet produced nothing. Clearly, there's a missing piece in this puzzle, something beyond our current models. Could magnetic fields, often overlooked in simulations, be the deciding factor, or are we witnessing the handoff between different types of central engines, where black holes sometimes fail to ignite the jets that power these bursts? What's fascinating is how this cosmic lottery reshapes our understanding of stellar life cycles. A star's fate isn't just about mass or age, it's about the subtle details written into its structure from birth. Details that determine whether its death will echo across the universe or fade quietly into the dark. Every failed GRB candidate is a clue, a reminder that even in destruction, nature follows rules we're still learning to read. And with each new observation, we get closer to predicting which stars will light the match and which will simply burn out. Some corners of the universe glow with gamma rays for no reason we can yet explain, regions where telescopes reveal nothing but empty blackness, yet detectors pick up a steady hum of high-energy light. This is the empty sky paradox, one of gamma-ray astronomy's most confounding puzzles. Imagine pointing a microphone at a silent forest and hearing a symphony, no instruments in sight, just music. That's the eerie situation scientists face when they map gamma-ray hotspots against optical and radio surveys, only to find glaring mismatches where the light has no obvious source. So what's lighting up these cosmic voids? One possibility lies in extreme objects hiding in plain sight. Take Blazar's supermassive black holes spearing jets of radiation directly at Earth. Normally, we'd spot their host galaxies, but some might be so distant or dust-choked that their visible light gets smothered, leaving only gamma rays as faint breadcrumbs. Then there's pulsars, the lighthouses of the cosmos. Older, slower spinning ones could emit gamma rays without the telltale radio pulses we use to identify them, effectively turning into invisible powerhouses. But here's the catch: even after accounting for these stealthy suspects, the numbers don't add up. There's simply too much unexplained radiation. That's where things get speculative and thrilling. Some theorists suggest we might be seeing the fingerprints of dark matter annihilation. If certain hypothetical particles like WIMP collide and destroy each other in deep space, the aftermath could include gamma rays. The empty sky might be teeming with these invisible interactions, a shadow universe revealing itself through high-energy sparks. Others propose even wilder ideas: cosmic strings, hypothetical defects in space-time from the Big Bang, could vibrate and release gamma radiation as they snap. Or maybe primordial black holes, those ancient leftovers from the universe's first moments, are evaporating in unseen corners, their final bursts of energy lighting up our detectors. Yet the most unsettling explanation might be the simplest: we're missing something fundamental about how gamma rays are produced. Current models assume certain emission mechanisms like particles accelerated by shock waves, but what if nature has another recipe we haven't imagined? Every unexplained photon nudges us to reconsider the rules, to question whether the cosmos holds exotic physics beyond our textbooks. What makes this mystery so persistent is its scale. These orphan gamma rays aren't rare flukes. They're a pervasive background whispering that our catalogue of cosmic phenomena is incomplete. With each new observatory, from the Fermi Gamma Ray Space Telescope to upcoming missions like the Cherenkov Telescope Array, scientists hunt for patterns, clusters, energy distributions, anything that might crack the case. But for now, the empty sky keeps its secrets, reminding us that sometimes the universe's loudest messages come from the quietest places. Pulsars are nature's precision timekeepers, cosmic lighthouses that sweep beams of radiation across space with clockwork regularity. Or at least they're supposed to, but scattered across the galaxy, a handful of these spinning neutron stars defy expectations, firing off gamma rays in erratic, hiccuping bursts that leave astronomers scratching their heads. These anomalous gamma-ray pulsars don't just break the rules, they rewrite them, forcing us to question how neutron stars accelerate particles to unimaginable energies. Take PSR J 2021 plus 4205, a pulsar that should be a textbook example. It spins 17 times a second, its magnetic field trillions of times stronger than Earth's perfect conditions for steady gamma-ray emission. Yet when scientists observed it with NASA's Fermi telescope, they caught something bizarre. Its gamma rays arrived in unpredictable splashes, flickering on and off like a faulty streetlight. No model of pulsar magnetospheres predicted this. If these stars are cosmic dynamos, their engines should run smoothly, not stutter. So what's jamming the gears? One theory points to crust quakes, sudden fractures in the neutron star's ultra-dense surface. Imagine a spinning ice skater tightening their arms, but every so often their jacket snags, disrupting the motion. These tiny stellar quakes could temporarily warp the magnetic field, altering how particles flow and creating those gamma-ray hiccups. There's just one problem: the timing doesn't always match. Some pulsars show delays between the quakes and gamma-ray changes, suggesting something deeper at play. Then there's the wild card: magnetic reconnection. Near the pulsar's poles, magnetic field lines might snap and reconnect, a process seen on the Sun during solar flares. These violent rearrangements could launch particle avalanches, producing sporadic gamma-ray bursts. But here's the catch: reconnection usually requires plasma, and neutron star magnetospheres were thought to be too orderly for such chaos. Unless, of course, we've underestimated how turbulent these environments truly are. The real curveball comes from the missing middle: pulsars, objects that emit gamma rays but lack the radio pulses we use to detect most neutron stars. Are these anomalies part of the same family, just viewed from a different angle? Or do they represent an entirely new class of objects where gamma rays are the only clue to their existence? Every erratic pulse is a reminder that neutron stars, for all their seeming simplicity, are anything but predictable. They're laboratories of extreme physics, where densities crush atoms into exotic matter and magnetic fields twist space itself. And when their gamma rays don't play by the rules, it's a sign we're missing a piece of the puzzle, perhaps one that could rewrite our understanding of the universe's most extreme environments. Deep in the heart of our galaxy, where stars crowd so tightly they form a glittering snowstorm around the supermassive black hole Sagittarius A*, astronomers have stumbled upon a glow that shouldn't be there. This is the Galactic Center excess, an enigmatic surplus of gamma rays radiating from the Milky Way's core, defying every attempt to pin down its source. At first glance, it looks like the smoking gun for dark matter, the very signal theorists predicted if invisible particles were colliding and annihilating in the darkness. But the cosmos rarely serves up easy answers, and this mystery is far from solved. Picture the scene. When researchers sifted through years of data from the Fermi Gamma Ray Space Telescope, they expected a certain baseline of gamma radiation from known objects, pulsars, cosmic rays slamming into gas clouds, the usual suspects. But stacked atop that background was an unexpected bump, a diffuse excess concentrated within about 5,000 light-years of the Galactic Center. Its energy signature, peaking around 2 giga-electronvolts, matched eerily well with predictions for dark matter particles like WIMP, weakly interacting massive particles, crashing together and dissolving into gamma rays. The distribution was even spherical, just what you'd expect if dark matter haloed the galaxy like an invisible fog. But then came the complications. When scientists zoomed in, they found the excess wasn't perfectly smooth. Tiny point sources speckled the signal, suggesting some of it might come from pulsars too faint to resolve individually. Millisecond pulsars, old neutron stars spun up to ludicrous speeds by stealing material from companions, are especially sneaky candidates. These cosmic vampires emit gamma rays steadily, and the Galactic Center is packed with them. Could thousands of these dim, unresolved objects mimic a dark matter signal? Simulations suggest it's possible, though the math leaves room for debate. Then there's the cosmic ray argument. The Galactic Center is a maelstrom of activity, with gas clouds, magnetic fields, and stellar winds creating perfect conditions for particle acceleration. If protons or electrons slam into interstellar gas at high enough energies, they too can produce gamma rays. Some researchers argue this conventional physics might explain the excess without invoking exotic particles. But critics counter that the energy spectrum doesn't quite fit. Cosmic ray interactions tend to make a messier, broader gamma ray signature than what's observed. The plot thickens when you consider alternative dark matter models. Maybe the particles aren't WIMP at all, but something stranger: actions, sterile neutrinos, or even particles that interact through unknown forces. Each twist in the theory leads to subtle differences in the expected gamma ray signal, sending physicists back to their chalkboards to recalculate. What makes this puzzle so captivating is its high-stakes implications. If the excess truly is dark matter, it'd be one of the most profound discoveries in modern physics, a direct window into the invisible scaffolding of the universe. But if it's just pulsars or cosmic rays, it's still a masterclass in how complex the cosmos can be, how even the brightest signals can wear masks. Every new observation, from radio surveys hunting hidden pulsars to next-generation gamma-ray telescopes, chips away at the mystery. For now, the Galactic Center keeps its secrets, a reminder that sometimes the universe's biggest questions lurk right in our own backyard. Beyond the comforting spiral of the Milky Way, the cosmic gamma-ray background holds another secret: it's not perfectly smooth. Instead, this high-energy light shows subtle ripples, patches where the glow brightens or dims in ways we still struggle to explain. This unevenness, called extragalactic anisotropy, is like looking at a map of the night sky and finding constellations no one taught you, patterns hinting at hidden structures woven into the fabric of the universe itself. At first glance, you might assume these variations trace the cosmic web, the vast network of galaxy clusters and dark matter filaments stretching across billions of light years. After all, gamma rays often come from violent environments, active galaxies with supermassive black holes, or regions where galaxies collide in spectacular mergers. But when scientists meticulously subtract known sources from the data, the map refuses to smooth out. Some patches remain stubbornly brighter, others eerily dark, as if an unseen hand painted over the canvas of space. One leading theory suggests we're seeing the ghosts of ancient blazars, active galaxies whose jets once pointed directly at Earth but have since faded or shifted direction. These beams, brighter than 1 trillion suns at their peak, could have left behind echoes in the form of lingering gamma-ray hotspots. Yet even stacking every known blazar from the universe's history into simulations can't fully replicate the observed pattern. There's simply too much residual structure, too many unexplained bright regions with no obvious counterparts in other wavelengths. Then there's the particle physics angle. Some theorists propose that dark matter, usually imagined as a uniform mist, might clump more than we thought on the largest scales. If these hypothetical particles occasionally collide and annihilate, their deaths could release gamma rays in sporadic, uneven bursts, creating a patchwork of light across the cosmos. Others speculate about primordial magnetic fields, relics from the universe's infancy, twisting and accelerating particles in ways that imprint irregularity on the gamma-ray sky. Perhaps the most tantalizing possibility is that this anisotropy reveals entirely new physics. Quantum fluctuations in the early universe, magnified by inflation, might have seeded not just galaxies but also vast, invisible structures, domains where the fundamental forces behave differently or where exotic particles congregate. The gamma-ray variations could be shadows of these colossal, hidden frameworks, etched into the high-energy light we observe today. What's striking is how subtle these signals are. Detecting them requires sifting through petabytes of data, separating the faintest whispers from the roar of known sources. It's a testament to our instruments like the Fermi Gamma-Ray Space Telescope that we can even perceive these nuances at all. Every tweak to the analysis, every improvement in resolution, peels back another layer, revealing how much we still don't understand about the universe's grand design. For now, the extragalactic gamma-ray background remains a cosmic Rorschach test, a pattern open to interpretation where each observer might glimpse a different story in its uneven glow. But one thing is certain, these fluctuations aren't random noise. They're clues waiting for the right key to unlock them. And when we do, we might just find that the universe's largest structures have been hiding in plain sight all along, written in the language of light we're only beginning to decipher. The universe loves a good game of hide and seek, especially when it comes to gamma rays. Among the countless points of light in the gamma-ray sky, some refuse to show their faces in any other wavelength. These are the dark gamma-ray sources, cosmic phantoms that blaze in high-energy light but leave no trace in radio, optical, or X-ray telescopes. It's like hearing a singer's voice but finding the stage empty, no microphone, no performer, just the echo of something unseen. Take Fermi J 1623.5-0246 for example. This gamma-ray hotspot, discovered by NASA Fermi telescope, pulses with energy, yet every attempt to locate its origin comes up blank. No galaxy, no neutron star, not even a wisp of gas to blame for the outburst. One possibility, a rogue supermassive black hole, ejected from its galaxy during a cosmic collision, now drifting through intergalactic space. Without a steady diet of stars or gas to light up its surroundings, such an object could fire gamma rays from its jets while remaining invisible in every other wavelength. Then there's the dark matter angle. If clumps of this mysterious substance lurk in certain regions of space, their particle collisions could theoretically produce gamma rays, no stars or black holes required. Simulations suggest dark matter halos around dwarf galaxies might glow faintly in gamma light, matching some of these unidentified sources. But there's a catch: the energy spectra often don't align neatly with predictions. Instead of the smooth bumps expected from dark matter annihilation, many sources show jagged, unpredictable emission lines, leaving researchers scratching their heads. Perhaps the most intriguing candidates are the hypothetical quark stars, objects even denser than neutron stars, where matter crushes down into a soup of free quarks. These theoretical oddballs could emit gamma rays through processes we've yet to model, vanishing in other wavelengths due to their exotic physics. Or consider the possibility of naked pulsars, neutron stars born without the usual debris fields, their gamma beams visible but their surroundings too barren to reflect light. What's fascinating is how these dark sources defy classification. Some flicker like active galaxies, others hum steadily like pulsars, and a few burst unpredictably, blending traits from multiple cosmic phenomena. It's as if the universe invented new rules just for them, rules we're still decoding. Every time a new telescope comes online, like the upcoming Cherenkov telescope array with its unprecedented sensitivity, scientists hope to unmask these phantoms. But for now, they remain cosmic riddles, reminding us that even in an age of advanced astronomy, the sky still holds shadows we can't yet illuminate. The deeper we look, the clearer it becomes. These aren't just gaps in our data. They're signposts pointing to physics we haven't discovered yet, hidden in plain sight behind a curtain of gamma rays. Whether failed stars, unknown particles, or something beyond current theory, each dark source is a whisper from the universe's edge, inviting us to look harder and think differently about the fabric of reality itself. Gamma rays traveling across the cosmos face an invisible barrier, a fog of starlight that's been accumulating since the first stars flickered to life. This is the extragalactic background light, a diffuse glow from all the stars and galaxies that have ever existed, and it acts like a cosmic sieve for high-energy photons. When gamma rays above a certain energy, around 1 tera-electronvolt or TeV, collide with this ancient starlight, they're supposed to vanish, absorbed in a shower of particles long before reaching us. It's why scientists call this the TeV gamma ray horizon, a boundary beyond which the universe should appear dark to our telescopes, but nature, as always, has other plans. Some ultra-high-energy gamma rays laugh at this limit, arriving from distances so vast they should have been obliterated en route. Take the Blazar TXS 0506 plus 056, whose photons clocked in at a staggering 20 tera-electronvolts, 20 times higher than the supposed cutoff, after traveling 7.6 billion light-years. That's like a bullet piercing a wall it should have disintegrated against. So how did these photons cheat death? One possibility is that our models of the extragalactic background light are incomplete. Maybe the fog is thinner than we think, with gaps that let occasional high-energy photons slip through. But detailed measurements from infrared telescopes suggest otherwise. The starlight density seems sufficient to block them. Then there's the quantum loophole. Photons might transform into hypothetical action like particles mid-journey, slipping past the starlight undetected before converting back into gamma rays near Earth. It's a cosmic sleight of hand, exploiting particle physics we've yet to fully understand. Supporters of this idea point to subtle irregularities in the energy spectra of some gamma ray bursts, small dips and bumps that could hint at this oscillation process. Skeptics, though, argue these features might just be statistical noise or artifacts of how telescopes collect data. But the wildest explanation: these photons aren't playing by standard physics at all. Some theorists suggest that spacetime itself might be slightly foamy at microscopic scales, a prediction of certain quantum gravity models. If true, this frothy structure could alter how gamma rays interact with the background light, effectively bending the rules just enough to let a few ultra-high-energy photons survive. It's a radical idea, but when the universe keeps handing you anomalies, sometimes you need radical solutions. What makes this mystery so compelling isn't just the defiance of expectations, it's the stakes. If these photons are surviving due to new physics, we're glimpsing cracks in our understanding of reality itself. Every anomalous detection forces us to reconsider the boundaries of known science, probing whether Einstein's relativity or quantum mechanics need tweaking at these extreme energies. Upcoming observatories like the Cherenkov Telescope Array aim to catch more of these rule-breaking photons, mapping their energies and origins with unprecedented precision. Until then, the TV horizon remains both a barrier and a beacon, challenging us to look deeper into the haze and question what we think we know about light's journey through the cosmos. Andromeda, our closest galactic neighbor, holds a secret, a vast, luminous halo of gamma rays stretching hundreds of thousands of light-years beyond its spiral arms. Unlike the Milky Way's Fermi Bubbles, which tower above and below the galactic plane, this glow envelops Andromeda symmetrically like a faint, shimmering shroud. The discovery made by the Fermi Gamma Ray Space Telescope caught scientists off guard. Why? Because Andromeda isn't just any galaxy, it's a near twin of our own Milky Way, yet its gamma-ray profile is strikingly different. At first, researchers suspected similar origins to the Fermi Bubbles. Perhaps Andromeda's supermassive black hole had a violent outburst in the past, or maybe a wave of star formation sent shockwaves through its halo. But the data told a different story. The gamma-ray emission is smoother, more evenly distributed, and lacks the sharp edges characteristic of explosive events. Instead, the leading explanation points to cosmic rays' high-energy particles, likely protons slamming into interstellar gas at nearly light speed. These collisions produce pions, short-lived particles that decay into gamma rays, creating the diffuse glow we observe. Here's the twist: Andromeda's gas content isn't dramatically higher than the Milky Way's, so why the brighter gamma-ray halo? One clue lies in its star-forming history. Unlike our galaxy, Andromeda experienced a major collision billions of years ago, stirring up its gas and triggering prolonged bursts of star birth. More stars mean more supernova, the cosmic accelerators that launch particles to extreme energies. Over time, these particles could have saturated Andromeda's halo, creating a lingering reservoir of cosmic rays that still light up in gamma rays today. But there's a darker possibility. Some theorists suggest the halo could be a sign of dark matter annihilation. If Andromeda's dark matter halo is denser or more concentrated than the Milky Way's, collisions between these elusive particles might produce gamma rays at a higher rate. The challenge: the signal lacks the telltale energy bump expected from dark matter decay, leaving the door open for alternative explanations. What makes this mystery so compelling is the comparison to our own galaxy. The Milky Way's gamma-ray structures are chaotic bubbles, filaments, and jets, while Andromeda's halo is serene and uniform. It's like comparing a fireworks display to candlelight. This disparity forces us to rethink how galaxies evolve and interact with their surroundings. Does Andromeda's calm exterior hide a turbulent past, or is the Milky Way the odd one out, its Fermi Bubbles a fluke of our black hole's hyperactivity? Every new observation peels back another layer, revealing how much we still don't understand about the lives of galaxies. Andromeda's gamma-ray halo isn't just a curiosity, it's a mirror, reflecting back questions about our own cosmic home. As telescopes grow more sensitive, we may yet find these halos are common. Their whispers of high energy light a universal signature of galactic life and death. Until then, the enigma of Andromeda's glow remains a tantalizing puzzle, one that challenges us to look deeper, not just across space, but into the very physics shaping the universe around us. Blazars are the cosmic lighthouses of the universe, supermassive black holes at the cores of galaxies, shooting jets of radiation directly toward Earth with such intensity they outshine entire galaxies. Yet for all their predictable brilliance, some blazars have a habit of misbehaving, erupting in gamma-ray flares so sudden and violent they challenge everything we know about how black holes feed. These aren't just gradual brightenings, some fire off in mere minutes, releasing more energy than our sun will produce in its entire lifetime. The question isn't just how, it's how so fast. Take Blazar PKS 2001-59-152, which in 2016 flared so unpredictably that astronomers scrambled telescopes worldwide to catch it. Its gamma-ray output doubled in under 5 minutes, an absurd feat when you consider the physics at play. Black hole jets are powered by accretion disks, swirling rings of superheated gas slowly spiraling inward. But here's the catch: accretion disks are huge, often wider than our solar system. Changes in their behavior should take days or weeks to propagate, not minutes. It's like revving a car engine and expecting the exhaust plume to instantly shift from idle to supersonic. So what's breaking the rules? One theory points to magnetic reconnection, a process where twisted magnetic field lines near the black hole snap and realign, unleashing pent-up energy like a cosmic rubber band. We've seen this on the sun during solar flares, but scaled up to black hole proportions, the energy release could be staggering. Simulations suggest these magnetic explosions might create tiny, ultra-hot pockets in the jet, acting like particle accelerators that funnel energy into gamma rays almost instantly. Then there's the jet within a jet hypothesis. Instead of a smooth flow, the black hole's outflow might contain smaller, hyperactive filaments, narrow streams of plasma spinning at near light speed. Turbulence in these filaments could trigger localized eruptions, explaining why some flares appear so brief and intense. Imagine a fire hose not spraying uniformly, but with intermittent geysers bursting from its surface. But the real curveball comes from the outliers, blazars like Mystyrk 501, which flare too regularly, pulsing like a metronome every few hours. No natural process in accretion disk should create such clockwork precision. Some theorists wonder if we're seeing the shadow of a second black hole, a smaller companion locked in a tight orbit, stirring the disk like a spoon in coffee and creating rhythmic disturbances. Others propose more exotic physics, like quantum effects near the event horizon, warping how energy escapes. What makes these flares so tantalizing is their sheer audacity. They defy not just our models, but our intuition about how cosmic objects should behave. Every anomalous burst forces us to reconsider the limits of gravity, magnetism, and particle physics. And with new telescopes like the Cherenkov telescope array coming online, we're on the verge of catching these eruptions in unprecedented detail, perhaps finally uncovering whether the fault lies in our theories or in the black holes themselves, playing by rules we've yet to write. For now, the flares remain cosmic paradoxes, brilliant reminders that even the most extreme objects in the universe can still surprise us. Stretching across the Milky Way like cosmic cobwebs, nearly invisible threads of gamma-ray light weave through the darkness, structures so faint they were only discovered by accident. These ghost filaments, some stretching hundreds of light years, defy easy explanation. They don't align with known supernova remnants or pulsar winds, and their eerie glow hints at forces we've yet to fully understand. Could they be the scars of ancient stellar explosions, lingering long after the visible debris has faded, or something far stranger, like dark matter unraveling along unseen magnetic fields? Take the Fermi Bubbles' smaller cousins, the so-called Fermi haze, filaments, thin tendrils of gamma rays curling near the Galactic Center. Unlike the colossal bubbles, these structures are delicate, almost wispy, as if etched into space by a fine cosmic brush. One leading theory suggests they're shockwaves from long-dead stars. Picture a supernova detonating millions of years ago, its blast wave carving through interstellar gas, accelerating particles to near light speed. Over eons, the visible remnants dissipate, but the high-energy particles linger, tracing the skeleton of that forgotten explosion in gamma rays. But there's a problem. Some filaments appear too straight, too organized, as if shaped by an invisible hand. This has led to more exotic explanations, like dark matter annihilating along dense streams in the Milky Way's halo. If dark matter clumps into narrow rivers through space, collisions within these channels could produce gamma rays in faint, linear patterns like glowing seams stitching through the galaxy's fabric. Simulations show it's possible, but the evidence remains circumstantial, like finding footprints without ever seeing the creature that made them. Then there's the magnetic mystery. Cosmic magnetic fields, though incredibly weak compared to Earth's, stretch across the galaxy, shaping how particles move. Some filaments align suspiciously well with these invisible force lines, suggesting they might be cosmic particle accelerators, natural versions of humanity's largest colliders. Electrons spiraling along magnetic field lines can emit gamma rays, creating luminous threads where the fields are strongest. Yet even this tidy explanation falters when faced with filaments that twist abruptly or branch like fractured lightning, defying the smooth arcs predicted by models. The most perplexing examples are the isolated filaments, floating far from any obvious energy source. These lone wolves, like the one near the constellation Cygnus, glow steadily without a supernova or black hole nearby to power them. Some researchers speculate they could be relic structures, echoes of events so ancient their origins have vanished from the observable universe. Others wonder if we're seeing the wake of a runaway black hole, plowing through gas clouds and leaving a trail of gamma rays in its path. What makes these filaments so compelling isn't just their mystery, it's their persistence. Unlike gamma-ray bursts or flares, which vanish in moments, the ghost filaments endure, subtly reshaping our understanding of the interstellar medium. They remind us that the galaxy isn't just empty space dotted with stars, but a dynamic ecosystem where energy flows in ways we're only beginning to map. Every new observation peels back another layer, revealing not just the violence of the cosmos, but its quiet, lingering artistry, a universe that writes its history in light we're still learning to read. Cosmic rays, those high-speed protons and atomic nuclei racing through space, should be the universe's most reliable gamma-ray factories. When these particles smash into interstellar gas, the collisions ought to produce a predictable cascade of secondary particles, including pions, which then decay into gamma rays. Scientists call this the hadronic process, and it's been a cornerstone of astrophysics for decades. But here's the catch: when researchers compare predictions to actual observations, the numbers don't line up. In some regions, the gamma-ray output falls suspiciously short. In others, it blazes brighter than expected. This cosmic ray/gamma-ray mismatch isn't just a minor accounting error. It's a glaring hint that our understanding of the interstellar medium, the very fabric of our galaxy, might be missing entire chapters. Consider the Good Belt, a ring of young stars and gas clouds wrapping around our solar neighborhood. According to cosmic ray flux measurements, collisions here should generate a steady hum of gamma rays. Yet when telescopes like Fermi scrutinize the region, they detect only about 60% of the expected signal, whereas the missing 40%. One possibility is that our maps of interstellar gas are incomplete. Hydrogen, the primary target for cosmic ray collisions, comes in two flavors, atomic H1 and molecular H2. Traditional radio telescopes spot H1 easily, but H2, which lacks a radio signature, often hides in plain sight. Could vast reservoirs of unseen molecular gas be absorbing cosmic rays without producing the expected gamma-ray payoff? Some studies suggest yes, but even after adjusting for this dark gas, the math still leaves gaps. Then there's the opposite problem, areas like the Cygnus X star-forming complex, where gamma rays pour in at roughly double the predicted rate. If cosmic rays are the painters, why is their gamma-ray brush dripping so much extra ink here? One compelling theory points to pevotrons, natural particle accelerators far more powerful than standard supernova remnants. These hypothetical objects, possibly powered by hypernova explosions or pulsar wind nebulae, might boost cosmic rays to energies beyond what typical models account for. At these extremes, particle collisions could produce gamma rays through rare or overlooked channels, skewing the totals. But the plot twist: some of the gamma-ray excesses align eerily with regions rich in atomic hydrogen, but poor in molecular gas, the exact opposite of what missing gas theories would predict. This has led researchers down a rabbit hole of alternative explanations, from tangled magnetic fields redirecting cosmic rays to unexpected particle diffusion rates. Imagine pouring water onto a sponge only for it to splash back at you. The interstellar medium might be warping cosmic ray paths in ways we haven't accounted for, scattering them into voids or concentrating them unpredictably. The boldest proposals venture beyond conventional physics. Could some gamma rays arise from the decay of exotic dark matter particles instead of pion production? Or does interstellar space contain unknown states of matter that alter how energy dissipates? Each anomaly forces us to reconsider the rules, testing whether our models are incomplete or whether the cosmos is playing by an entirely different playbook. What makes this mismatch so pivotal is its universality. These discrepancies aren't confined to a few odd corners of the galaxy. They're woven into the Milky Way's broader gamma-ray tapestry. Every unresolved gap whispers that our cosmic neighborhood is more complex, more dynamic than textbooks describe. With next-generation telescopes like the Cherenkov Telescope Array poised to map these interactions in unprecedented detail, we might finally crack the code, revealing whether the fault lies in our instruments, our equations, or the universe's stubborn refusal to conform to expectations. Until then, the cosmic ray/gamma ray mismatch stands as a quiet rebellion against our assumptions, proving that even the most fundamental processes in space can still surprise us. The Fermi Gamma Ray Space Telescope has mapped the sky in high-energy light, cataloging thousands of sources, yet nearly a third of them refuse to reveal their true identities. These aren't just dim objects lurking at the edge of detection. They're bright, unambiguous gamma-ray signals with no visible counterparts in radio, optical, or X-ray telescopes. It's like having a phone full of contacts with no names attached, numbers that keep calling, but whose faces remain a mystery. Take Fermi Source 3 FGLJ1616.1-5184, a steady gamma-ray beacon near the galactic plane. Despite years of searching, not a single pulsar, black hole, or galaxy aligns with its position. One tantalizing possibility: a radio-quiet pulsar, a neutron star whose lighthouse-like beams don't sweep past Earth in radio waves but still emit gamma radiation through other mechanisms. These cosmic misfits could be spinning down after a violent youth, their magnetic fields too weak to produce the classic radio pulses we use to spot them. Then there's the dark horse candidate, isolated black holes. Most stellar mass black holes reveal themselves by tearing material from companion stars, creating bright accretion disks. But a rogue black hole drifting alone through interstellar space might only betray its presence through rare gamma-ray flares, perhaps from stray gas clouds falling into its gravitational clutches. Simulations suggest there could be millions of these dark wanderers in our galaxy, their occasional gamma-ray burps lighting up Fermi's detectors before fading back into obscurity. But the real enigma arises when you consider the most exotic explanations. Some unidentified sources cluster in regions where dark matter is predicted to concentrate, like dwarf galaxies or the Milky Way's halo. If dark matter particles annihilate upon collision, they could produce gamma rays with distinct energy signatures. The trouble is, these theoretical signals often look frustratingly similar to those from mundane astrophysical objects. It's like trying to distinguish a whisper in a roaring stadium. The hints might be there, but the noise drowns them out. Even stranger are the sources that flicker unpredictably, defying the steady glow of pulsars or the predictable flares of active galaxies. A handful of these objects, like Fermi J0500 plus 0039, brighten and dim without apparent rhythm. Could they be magnetar neutron stars with ludicrously strong magnetic fields undergoing sporadic crust quakes? Or perhaps evidence of quark nova, theoretical explosions where neutron stars collapse further into denser quark stars, releasing torrents of gamma rays in the process? The challenge isn't just identifying these objects, it's accepting that some might represent entirely new astrophysical phenomena. History offers a sobering lesson. Before pulsars were discovered in 1967, their rhythmic radio bursts were briefly mistaken for alien signals. Today's unidentified gamma ray sources could be tomorrow's groundbreaking discoveries, hiding physics we've yet to imagine. With each passing year, new telescopes and analysis techniques chip away at the mystery. Cross-referencing Fermi's data with infrared surveys has unmasked a few sources as dust-shrouded galaxies, while others have been linked to faint, distant pulsars. Yet the stubborn remainder persists, a gallery of cosmic strangers reminding us that for all our progress, the universe still holds cards close to its chest. Whether orphaned stellar remnants, dark matter's calling card, or something beyond current theory, these enigmatic sources are more than gaps in our knowledge. They're invitations to look deeper, to question harder, and to embrace the thrill of the unknown. Some cosmic explosions refuse to fade quietly into the night. Centuries after the light of a supernova first reaches Earth, strange gamma-ray echoes occasionally ripple across detectors, delayed signals that shouldn't exist if light alone were at play. These afterglows don't match the expected decay curves of radioactive elements or shockwave remnants. Instead, they flicker back to life months or even years later, as if something unseen is reigniting the aftermath of stellar cataclysms. Could these be literal light echoes, photons bouncing off interstellar dust clouds long after the initial blast? Or is the universe hinting at entirely new physics hidden within these ghostly reverberations? Take supernova 2508d, whose gamma-ray emission inexplicably brightened again 400 days after the explosion, long after its shockwave should have dissipated. Traditional models chalk this up to light echoes, where radiation from the original blast finally reaches us after zigzagging through cosmic dust. But here's the problem. The gamma-ray revival didn't align with the infrared dust signatures expected for such scattering. Instead, the energy spectrum bore an uncanny resemblance to pion decay, a signature of fresh particle collisions. It's as if the supernova's corpse kept accelerating cosmic rays long after its death, a cosmic engine refusing to shut off. Then there's the neutron star merger GW100 and 717, detected via gravitational waves in 2017. Its gamma-ray afterglow didn't just fade predictably, it pulsed erratically for nearly 1,000 days. One radical explanation: the collision left behind a rapidly spinning magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth. Such an object could channel rotational energy into particle jets, producing late-time gamma-ray surges as its magnetic field gradually unwound. Yet even this theory struggles to explain the irregular timing. Magnetar-powered afterglows should smooth out, not stutter like a dying flashlight. Darker possibilities lurk in the shadows. Some theorists propose these echoes stem from action-like particles, hypothetical, nearly massless entities predicted by string theory. If present, they could convert back into gamma rays when encountering magnetic fields far from the original explosion, creating phantom signals disconnected from the initial event. Others speculate about primordial black holes, remnants of the Big Bang, passing through supernova remnants and triggering fresh particle acceleration as they siphon gas. The most tantalizing clue lies in the echo delays themselves. For certain supernova, the lag between explosion and gamma-ray resurgence matches the time it would take neutrinos, those ghostly, barely interacting particles to traverse the debris and trigger cascades of secondary interactions. If confirmed, this would mean we're glimpsing a hidden neutrino universe where these elusive particles act as cosmic messengers, delivering energy to distant regions of the wreckage long after the visible fireworks end. Every anomalous echo forces astronomers to reconsider the life cycles of stellar explosions. These aren't just one-and-done events, but dynamic processes with extended aftermaths we're only beginning to decode. With next-generation neutrino detectors and gamma-ray telescopes coming online, we may finally learn whether these delayed signals are cosmic illusions or the first murmurs of physics waiting beyond the standard model. Until then, they remain temporal riddles written in light that travels through time as much as space. Galaxies are supposed to follow the rules active galactic nuclei light up gamma-ray telescopes with their blazing jets, while pulsars and supernova remnants contribute their own high-energy signatures. But scattered across the cosmos, some star-forming galaxies break the mold, emitting a strange, diffuse gamma-ray glow that shouldn't be there. This isn't radiation from their central black holes or spinning neutron stars. It's a pervasive fog stretching far beyond the usual hotspots, as if the entire galaxy is humming with hidden energy. Take the Whirlpool Galaxy, a picturesque spiral neighbor actively birthing new stars. When gamma-ray telescopes turned their gaze toward it, they expected to see pinpoint sources, maybe a few pulsars or the faint imprint of an aging supernova. Instead, they found something far more intriguing, a soft, uniform glow enveloping its spiral arms, unrelated to any known compact object. This isn't an isolated case. Galaxies like M82, a starburst powerhouse churning out stars at a frenzied pace, show similar gamma-ray halos with emissions far exceeding what classic cosmic ray models predict. So where's all this excess energy coming from? The prime suspect is cosmic rays on overdrive particles accelerated to extreme speeds by the relentless churn of star formation. In galaxies like these, supernova explode hundreds of times more frequently than in placid spirals like the Milky Way. Each blast launches shockwaves through interstellar gas, turning the galaxy into a giant particle accelerator. But here's the twist. When scientists tally up the expected gamma rays from these cosmic ray collisions, they still fall short of the observed glow. There's a missing multiplier in the equation. One theory points to overlooked turbulence in the interstellar medium. Normally, cosmic rays lose energy slowly as they traverse the galaxy. But in star-forming regions, chaotic magnetic fields and colliding gas clouds might trap particles longer, forcing them to ricochet endlessly until they've piled up enough energy to produce extra gamma rays. Picture a pinball machine set to maximum tilt. The particles don't just bounce, they linger, gaining intensity with each passing moment. Then there's the dark horse explanation, protostellar jets. Young, massive stars often launch powerful outflows as they form, streams of plasma that could accelerate particles to gamma-ray emitting energies. These jets are usually too faint to spot individually, but collectively they might saturate a galaxy's outskirts with diffuse radiation. It's like standing in a field of fireflies, each one dim on its own, but together they light up the night. But the real wildcard, dark matter, might still have a role. If certain types of weakly interacting particles cluster in star-forming galaxies, their annihilations could contribute to the gamma-ray fog. The challenge is separating this signal from the astrophysical noise, like trying to hear a whisper in a windstorm. What makes this mystery so compelling is its universality. The gamma-ray excess isn't limited to a few oddball galaxies. It's a pattern repeated in starbursts across the cosmos. Every new observation forces us to reconsider how energy flows through these dynamic systems, whether we've underestimated the chaos of star formation, missed hidden particle accelerators, or stumbled onto something entirely unexpected. As telescopes grow sharper, the answers may finally come into focus, revealing whether these galaxies are simply louder versions of our own, or cosmic laboratories where the rules of physics bend in ways we're only beginning to glimpse. The Milky Way blazes with gamma rays, its spiral arms alive with pulsars, supernova remnants, and cosmic ray collisions. Yet just next door, Andromeda, our nearest galactic neighbor and a near twin in size and structure, glows faintly in comparison, its gamma ray output a mere fraction of what models predict. This quietness isn't just a curiosity, it's a cosmic contradiction, challenging our assumptions about how galaxies produce and trap high-energy radiation. If both galaxies are stuffed with stars, gas, and black holes, why does one shout in gamma rays while the other whispers? Start with cosmic rays, the high-speed protons and atomic nuclei blamed for most galactic gamma rays. When these particles collide with interstellar gas, they spawn pions that decay into gamma photons, creating a predictable background glow. In the Milky Way, this process lights up our galactic plane like a neon sign. But Andromeda's gas reservoirs aren't drastically smaller, and its star formation rate, though lower, doesn't fully explain the shortfall. Something's either stifling cosmic ray production or letting them slip away before they can generate gamma rays. One clue lies in Andromeda's magnetic architecture. Recent radio observations reveal its magnetic field is strangely disordered, lacking the large-scale coherence seen in the Milky Way. Without organized field lines to corral them, cosmic rays might escape into intergalactic space before colliding with enough gas to make gamma rays. Picture a sprinkler system with half its pipes broken. Water sprays everywhere but fails to water the garden. Similarly, Andromeda's cosmic rays could be leaking out, leaving its gamma ray harvest sparse. Then there's the black hole factor. The Milky Way's supermassive black hole, Sagittarius A star, may be quieter now, but its past outbursts like those that carved the Fermi Bubbles could have pumped the galaxy full of long-lived cosmic rays. Andromeda's central black hole, by contrast, shows no signs of such historical tantrums. Without those violent injections, its cosmic ray population might never have reached the densities needed for a gamma ray boom. But the plot thickens when you compare Andromeda to other gamma-ray-quiet galaxies like the Somma Spiral M33. These underperformers share traits: lower star formation, weaker magnetic fields, and oddly distributed gas. Yet even among them, Andromeda stands out. Its gamma-ray deficit is so stark that some researchers suspect an unseen population of cosmic ray cooling regions, areas where dense gas or turbulent magnetic fields sap particles' energy before they can produce gamma rays. The implications stretch beyond local galaxies. If cosmic rays routinely escape certain galactic environments, it could reshape how we model the universe's high-energy budget. Astronomers often use gamma rays as a proxy for cosmic ray density. But what if some galaxies are stealthily ejecting these particles into the voids between them? The cosmos might be threaded with invisible rivers of cosmic rays, undetectable except by their absence. For now, Andromeda's hush remains a puzzle, one that future telescopes like the Cherenkov Telescope Array aim to solve. Each new observation peels back another layer, revealing not just how galaxies shine, but how they hide their light, and what those silences can teach us about the forces shaping our universe. Gamma rays aren't just a distant cosmic phenomenon. Some of the most puzzling excesses glow startlingly close to home. Scattered across our solar neighborhood, mysterious hotspots pulse with high-energy light, defying easy explanation. Unlike the Milky Way's grand gamma-ray structures, these anomalies are intimate, almost personal, lurking within a few hundred light-years of Earth. Some align eerily with the solar system's motion through space, while others cluster in regions suspiciously rich with hypothetical dark matter. Could these be traces of invisible cosmic interactions, or simply overlooked astrophysical processes playing out in our backyard? Start with the Fermi Bubbles' little sibling, a faint gamma-ray glow detected along the solar system's path around the galaxy. As the Sun orbits the Milky Way's core, it plows through interstellar gas and dust, creating a bow shock akin to a boat's wake. Normally, this wouldn't produce detectable gamma rays, but recent Fermi telescope data reveals an unexpected excess trailing our motion. One provocative theory suggests the Sun's magnetic field might act like a particle accelerator, ramping up cosmic rays to energies where collisions with interstellar gas spark gamma-ray flares. It's as if our star, usually a passive traveler, leaves a faint radioactive fingerprint in its wake. Then there's the curious case of the good belt hotspots, patches of gamma-ray brightness overlapping with this local ring of young stars and gas clouds. Standard models attribute the glow to cosmic rays slamming into interstellar hydrogen, but the intensity doesn't match predictions. Some researchers speculate dark matter could be the culprit. Simulations suggest our galaxy's halo might contain dense subhalos, invisible clumps of dark matter drifting like icebergs in a cosmic sea. If these clumps decay or collide, they could release gamma rays precisely where telescopes detect unexpected excesses. The challenge proving it: these signals lack the smoking gun energy spikes expected from dark matter annihilation, leaving room for skeptics to argue for mundane origins like hidden supernova remnants or undetected pulsars. The most tantalizing enigma lies in the direction of the constellation Draco, where gamma-ray detectors pick up an unusual concentration of high-energy photons. Draco hosts several dwarf galaxies, dark matter-rich satellites of the Milky Way, leading to fevered speculation that we're glimpsing the first hints of particle decay from the universe's most elusive substance. Yet alternative explanations persist. Could ancient supernova have left behind cosmic ray reservoirs, pockets of trapped particles slowly leaking gamma rays over millennia? Or are we seeing the aftermath of a nearby stellar cataclysm, like a neutron star merger whose shockwaves recently reached Earth? What makes these local hotspots so compelling is their accessibility. Unlike distant gamma-ray bursts or blazars, these anomalies are close enough to study in unprecedented detail. New missions like the upcoming Amigo telescope aim to map them with finer resolution, potentially revealing whether they're cosmic signposts pointing to dark matter, or just the universe's way of reminding us that even familiar celestial neighborhoods hide surprises. Until then, these nearby glows remain a paradox, the most intimate of cosmic mysteries, waiting patiently in our own stellar backyard. Tiny, dim, and seemingly insignificant dwarf spheroidal galaxies might be the last place you'd expect cosmic fireworks, yet these faint stellar islands hold some of the universe's most tantalizing gamma-ray secrets. Unlike their larger, flashier cousins, dwarf galaxies lack the star-forming frenzy and supermassive black holes that typically generate high-energy radiation. But when scientists pointed gamma-ray telescopes like Fermi toward these cosmic backwaters, they detected something unexpected: a faint, persistent glow that refuses to fit neatly into any astrophysical box. Is this the long-sought signature of dark matter annihilation, or just another cosmic red herring? Consider the case of Reticulum 2, a dwarf galaxy so sparse it contains barely 1,000 stars. Despite its quiet demeanor, Fermi detected a subtle gamma-ray excess from its direction, one that aligns eerily with predictions for dark matter particles colliding and dissolving into radiation. The logic is compelling. Dwarf galaxies are thought to be drowning in dark matter, with mass-to-light ratios hundreds of times higher than the Milky Way's. If dark matter exists in the form of weakly interacting massive particles, WIMP, their mutual annihilation should produce gamma rays precisely in the energy range observed. It's like finding candlelight in a windowless room, a hint that something invisible is flickering in the dark. But the cosmos rarely serves up clean answers. Alternative explanations lurk in the shadows. Some of these gamma-ray whispers might come from pulsars, neutron stars too old and slow to emit the telltale radio pulses we use to identify them. Others could stem from cosmic rays interacting with interstellar gas, a process that mimics dark matter signals. The challenge is statistical. With so few stars and so little gas in these dwarfs, even one or two undetected pulsars could skew the entire gamma-ray budget. It's like trying to hear a pin drop in a quiet room, only to realize the faint taps might just be your own heartbeat. The debate intensifies when you examine the energy spectra. Dark matter annihilation should produce a smooth, predictable gamma-ray bump at specific energies depending on the particle's mass. Some dwarfs, like Draco and Ursa Minor, show tantalizing hints of such bumps, but the signals are too faint to claim victory. Meanwhile, other dwarfs with similar dark matter content show no gamma rays at all, a contradiction that keeps theorists up at night. If dark matter is uniform, why do some dwarfs glow while others stay dark? Adding fuel to the fire are recent observations of ultra-faint dwarf galaxies so dim they were only discovered in the past decade. These cosmic ghosts, like Triangulum 2, show gamma-ray excesses even more pronounced than their larger counterparts. Yet they also harbor bizarre stellar populations with stars that appear strangely clustered. Could ancient, unseen supernova have left behind cosmic ray accelerators that still pump out gamma rays today? Or are we seeing the first whispers of a dark matter particle lighter or more complex than traditional WIMP? The stakes couldn't be higher. If these gamma rays truly stem from dark matter, it would rank among the most profound discoveries in physics, a direct window into the invisible 85% of the universe's mass. But if they're just astrophysical noise, they represent a cosmic prank of epic proportions, sending scientists down decades of dead-end theories. Future telescopes, like the Cherenkov Telescope Array, aim to settle the debate with sharper sensitivity and energy resolution. Until then, these faint glows remain cosmic Rorschach tests, revealing as much about our hopes as they do about the universe's hidden architecture. One thing's certain: the quietest corners of the cosmos often hold the loudest surprises. Peering back to the dawn of time, when the universe was a mere toddler of a few 100 million years old, astronomers have spotted something extraordinary: lighthouses of gamma rays blazing across the cosmos from incomprehensible distances. These high redshift sources, their light stretched and reddened by billions of years of cosmic expansion, shouldn't exist in conventional models. The early universe was a sparse place, with galaxies still in their infancy and black holes barely formed. Yet somehow, these gamma-ray beacons shine with an intensity that rivals modern quasars, as if the cosmos cheated by switching on its high-energy floodlights far too early. What cosmic powerhouses could possibly fuel them? One radical contender: primordial black holes, hypothetical relics forged in the seething chaos of the Big Bang itself. Unlike the black holes we know born from collapsing stars, these ancient anomalies could have formed from random density fluctuations when the universe was less than a second old. Ranging in size from a mountain's mass to thousands of suns, they might have littered the early cosmos like invisible embers, slowly devouring nearby gas and spewing gamma rays as they fed. If just a fraction of these primordial monsters survived to the epoch we're observing, their violent feasts could explain the mysterious gamma-ray lighthouses. The smoking gun, their light curves might flicker unpredictably, lacking the steady accretion signatures of later supermassive black holes. But there's another, even more exotic possibility: the first generation of supermassive stars, behemoths hundreds of times heavier than our Sun. Born in pristine clouds of hydrogen and helium before heavier elements polluted stellar nurseries, these stars would have burned hot and fast, collapsing directly into black holes within a few million years. Their deaths wouldn't be ordinary supernova, but hyper-explosive events called pair instability supernova, capable of lighting up the early universe with gamma-ray afterglows visible across billions of light years. A single such star could outshine an entire galaxy, its gamma-ray echo lingering like a cosmic flare gun shot into the void. the real puzzle lies in the timing. Some of these gamma-ray sources appear at redshifts above 7, meaning we're seeing them as they were when the universe was less than 800 million years old. That's barely enough time for gas to coalesce into galaxies, let alone nurture supermassive black holes weighing billions of suns. Unless, of course, the seeds of these monsters formed differently, perhaps via direct collapse of giant gas clouds skipping the star formation stage entirely. These dark stars, powered by particle annihilation rather than fusion, could have grown to immense sizes before collapsing into black holes, jump-starting gamma-ray production shockingly early. Detecting these lighthouses is only half the battle. Their spectra, the precise fingerprints of their light, could hold the key to distinguishing between these theories. Primordial black holes might imprint sharp, erratic spikes in their emission, while supermassive star remnants could leave smoother thermal signatures. Future telescopes like the James Webb Space Telescope, paired with gamma-ray observatories, aim to dissect these distant glimmers in unprecedented detail. What's at stake isn't just the identity of a few cosmic oddballs. If primordial black holes exist, they could solve multiple mysteries at once, perhaps even accounting for some of the universe's missing dark matter. And if supermassive stars dominated the early cosmos, they'd rewrite the story of how galaxies evolved, proving that the first structures grew not slowly, but in explosive, high-energy bursts. The gamma-ray lighthouses of the deep past aren't just anomalies, they're time capsules carrying clues to the universe's most formative moments. Every photon that reaches us from these ancient beacons is a message scrambled across 13 billion years, waiting for us to decode its secrets. Galactic collisions should be cosmic demolition derbies, chaotic, violent, and dazzling with high-energy fireworks. Yet when telescopes like Fermi peer into the hearts of merging galaxies, they catch something even stranger: vast tides of gamma rays sweeping across the wreckage like invisible tsunamis. These aren't the concentrated jets of active black holes or the pinprick flashes of supernova. They're diffuse, pervasive glows clinging to the spiral arms and tidal tails of galaxies mid-collision, as if the act of merging itself has set the universe's most energetic light simmering across millions of light years. Take the antennae galaxies, two spirals locked in a slow-motion crash for the past 300 million years. As their stars and gas twist into colossal arcs, Fermi detected gamma rays suffusing the entire collision zone, far exceeding what their supernova and pulsars should produce. One explanation: shock waves, immense ripples in the interstellar medium as gas clouds slam together at hundreds of kilometers per second. These collisions could act like natural particle accelerators, boosting cosmic rays to energies where their collisions with hydrogen atoms spark gamma-ray tsunamis. It's like watching ocean waves crest, except instead of water, it's the fabric of space itself churning with invisible energy. But the plot thickens when you examine galaxies like NGC 2372, another merging pair where gamma rays cluster suspiciously in dark matter-rich regions. Unlike the antennae's shock-focused emission, here the glow aligns with gravitational lensing maps areas where unseen mass bends the light of background stars. This has led to a tantalizing hypothesis. Could these gamma-ray tides be the echoes of dark matter particles annihilating as galaxies collide? Simulations suggest mergers might compress dark matter halos, increasing particle collision rates. If true, we're witnessing the invisible scaffolding of the universe briefly flickering into visibility, like a hidden ink revealed under cosmic ultraviolet light. Yet skeptics raise a crucial counterpoint. The gamma-ray spectra from these mergers often lack the sharp energy bumps predicted by popular dark matter models. Instead, they resemble the messy signatures of astrophysical processes, cosmic rays plowing into dense gas or turbulent magnetic fields reconnecting. Even more confounding, some colliding galaxies, like the mice galaxies NGC 4670 and 6668, show almost no gamma rays at all despite violent interactions. If mergers universally trigger dark matter signals, why the silence? The answer might lie in timing. Gamma-ray tides could be transient, flaring up during specific phases of a collision. Early on, as galaxies first graze each other, shock waves might dominate. Later, as their dark matter halos begin to merge, annihilation signals could peak. By studying mergers at different stages, from initial approach to final coalescence, scientists hope to decode this sequence. Upcoming radio telescopes like the Square Kilometre Array could map the cosmic ray distribution in these systems, while gamma-ray observatories hunt for spectral clues. What makes these gamma-ray tides so mesmerizing isn't just their origins, it's what they reveal about cosmic evolution. Galaxy mergers were once thought to be mere reshufflings of stars and gas. Now we see they're also laboratories for extreme physics, where invisible forces leave faint signatures in light we're only beginning to understand. Every collision is a test case, a chance to ask, are we seeing dark matter's grand unveiling, or just the universe's knack for hiding its most ordinary processes in plain sight? The tides roll on, carrying answers and deeper mysteries in their wake. Deep in the heart of our galaxy, miniature monsters lurk. Black holes no heavier than a few suns, yet capable of cosmic-scale violence. These aren't the supermassive giants anchoring galaxies. They're microquasars, stellar mass black holes or neutron stars with a bad habit of stealing material from companion stars and spitting it back out as relativistic jets. While their larger cousins, quasars, blast energy across billions of light-years, microquasars operate on a far smaller stage. Yet when it comes to gamma rays, they punch far above their weight, flickering unpredictably like candle flames in a cosmic draft, and that flickering is rewriting our understanding of how jets work. Take SS433, the Godzilla of microquasars. This binary system, located about 23,000 light-years away, fires jets at 90% the speed of light as its black hole devours a nearby star. When gamma-ray telescopes trained their sights on it, they expected steady, rhythmic emission particles accelerating smoothly along the jet's magnetic highways. Instead, they caught erratic bursts with gamma-ray output swinging wildly over hours or even minutes. It's as if someone kept flipping a cosmic switch, turning the jet's particle accelerator on and off at random. The culprit, turbulence, where we least expected it. Jets were long thought to be streamlined, with magnetic fields acting like orderly rails guiding particles to near light speeds. But microquasars reveal a messier truth. Their jets may be riddled with knots, regions where magnetic fields tangle and snap, triggering violent reconnection events. Picture a highway where sections of the road keep collapsing, forcing cars to lurch forward in fits and starts. These disruptions could explain the flickering, as particles caught in magnetic whirlpools suddenly gain explosive energy before being flung outward. Even stranger is the energy mismatch. Some microquasar gamma-ray flares peak at energies far beyond what standard shock acceleration should produce. One radical idea involves shear acceleration, where particles gain energy not from shocks, but by surfing the velocity gradient between the jet's fast inner spine and slower outer layers. It's like a surfer catching speed by zigzagging between ocean currents moving at different paces. If confirmed, this mechanism could upend decades of jet physics, proving nature has more than one way to rev particles to extreme energies. The real puzzle lies in the timing. Some microquasars, like V404 Cygni, flare in gamma rays before their jets visibly erupt in radio waves, a sequence that defies conventional models where particle acceleration happens downstream. Could the flares originate deep in the nozzle of the jet near the black hole itself? Or are we seeing feedback loops where gamma rays produced in the jet interact with the accretion disk, triggering fresh outbursts in a self-sustaining cycle? These tiny powerhouses aren't just scaled-down quasars, they're laboratories for extreme physics, offering a front-row seat to processes we'd never glimpse in their supermassive cousins. Their flickering gamma rays are more than just cosmic static. They're encrypted messages about how black holes, big and small, bend space, time, and energy to their will. And with every erratic pulse, they remind us that even the smallest monsters in the universe still have secrets to spill. Look toward the center of the Milky Way, and you'd expect a blinding gamma-ray glow, a torrent of high-energy light from supermassive black holes, pulsars, and cosmic ray collisions. But something peculiar happens when astronomers map this region. Patches of the gamma-ray sky appear dimmer than they should be, as if vast cosmic curtains are blocking the light. These aren't mere gaps in the data. They're gamma-ray shadows, regions where the Milky Way's own structure gets in the way of its radiation. The twist. These shadows reveal secrets about the invisible scaffolding of our galaxy, the clumpy, magnetized gas that shapes the passage of light itself. Take the Cygnus cocoon, a star-forming region about 4,500 light-years away. When gamma-ray telescopes scanned this area, they found a noticeable dip in emission, coinciding exactly with dense clouds of molecular hydrogen. Here's the catch. Gamma rays are supposed to barrel straight through ordinary gas like bullets through tissue paper. So why the shadow? The answer lies in cosmic rays, high-speed particles that generate gamma rays when they collide with interstellar gas. If a gas cloud is thick enough, it can act like a cosmic sponge, soaking up incoming cosmic rays before they have a chance to produce gamma rays on the far side. The result, a gamma-ray silhouette, a high-energy negative image of the cloud itself. But not all shadows play by these rules. Some, like the one near the Galactic Center, appear too large and diffuse to be explained by gas alone. Enter magnetism. The Milky Way's magnetic field, though a million times weaker than Earth's, weaves through space like an invisible spiderweb. In certain regions, these field lines may deflect cosmic rays away, preventing them from reaching gas clouds where gamma-ray production would occur. It's like a magnetic force field diverting a river. No water reaches the valley downstream, leaving it parched. These magnetic shadows hint at a dynamic interplay between particles and fields, one that's nearly impossible to map directly but leaves its mark in the gamma-ray light we do or don't see. The real enigma comes when shadows appear where they shouldn't. The Taurus molecular cloud, for instance, blocks more gamma rays than its gas density should allow. One provocative explanation: dark matter might be muddying the waters. If unseen particles lurk in these clouds, they could absorb or scatter cosmic rays without leaving a trace in other wavelengths. Alternatively, the clouds might harbor nests of old pulsars, dead neutron stars whose gamma-ray beams no longer point toward Earth, but whose presence stifles incoming cosmic rays like trees breaking the wind. What makes these shadows so valuable is their dual nature. They're not just absences, they're templates revealing the structure of the galaxy's hidden machinery. By studying where gamma rays vanish, astronomers can reverse engineer the properties of the interstellar medium, its density, its magnetic turbulence, even its dark matter content, with precision no other method allows. Every shadow is a cosmic X-ray, exposing the bones of the Milky Way in silhouette. And as telescopes grow sharper, these high-energy voids may yet unveil the galaxy's most closely guarded secrets, not by the light they emit, but by the light they steal. For decades, gamma rays stood alone as messengers of the universe's most violent events: blazars flaring, black holes merging, stars exploding in spectacular fireballs. But now, they're no longer solitary voices. The rise of multimessenger astronomy, detecting cosmic phenomena through gravitational waves, neutrinos, and light simultaneously, has transformed gamma-ray mysteries into even deeper puzzles. Some signals align perfectly with theoretical predictions, while others defy explanation entirely, leaving scientists grappling with a new era of cosmic contradictions. Take the case of gamma-ray burst GRB 170817A. When this colossal explosion lit up telescopes in 2017, it wasn't just the gamma rays that caught attention. For the first time, gravitational waves rippled in alongside the light, confirming the burst came from two neutron stars colliding. The event, dubbed GW170817, was a triumph proof that these cosmic crashes produce both gravitational ripples and gamma-ray fireworks. But here's the twist: the gamma-ray signal was oddly faint, a mere whisper compared to what models predicted. If neutron-star mergers are supposed to be gamma-ray powerhouses, why did this one underperform? Some theories suggest the jet might have been off-axis, pointed just slightly away from Earth, dimming its brilliance. Others propose the merger formed a hypermassive neutron star that delayed its collapse into a black hole, stifling the gamma-ray output. The Multimessenger data didn't solve the mystery, it deepened it, revealing gaps in our understanding of how these cataclysms unfold. Then there's the neutrino enigma. In 2017, the ice cube detector in Antarctica spotted a high-energy neutrino, a ghostly particle from deep space, whose path traced back to a flaring blazar, TXS 0506+056. Fermi confirmed the blazar was blazing gamma rays at the same time, seemingly closing the case. Active galaxies can accelerate particles to energies capable of producing both neutrinos and gamma rays. But when researchers combed through years of data, they found a troubling mismatch. Only a handful of neutrino events aligned with gamma-ray sources, despite the cosmos teeming with high-energy emitters. If blazars are neutrino factories, why aren't they flooding our detectors? The answer might lie in the jets themselves. Perhaps only specific magnetic field configurations or shock structures within them can generate neutrinos, making these detections rare. Or maybe neutrinos are produced in regions obscured by gas, their gamma-ray counterparts absorbed before reaching us. Either way, the Multimessenger era has turned what should be a straightforward link into a labyrinth of dead ends and false starts. Even more perplexing are the orphan signals, gravitational waves or neutrinos with no gamma-ray counterpart at all. The binary black hole merger GW150914, for instance, sent ripples through space-time in 2015, but gamma-ray telescopes saw nothing. Black holes merging in a vacuum shouldn't produce light, yet some theorists speculate that surrounding gas or magnetic fields might spark faint gamma-ray flashes. The absence of such a signal challenges these ideas, forcing physicists to reconsider how black holes interact with their environments. Similarly, neutrino alerts like IC 170922 arrive without any obvious gamma-ray source, as if the universe has invisible particle accelerators operating in the dark. What's emerging from this data is a cosmic Rorschach test, a pattern of contradictions that defies simple interpretation. The Multimessenger era hasn't just clarified gamma-ray mysteries, it's shattered old assumptions, revealing a universe far more nuanced and unpredictable than we imagined. Every neutrino or gravitational wave that matches a gamma-ray source feels like a victory, while every mismatch opens a door to new physics. And as detectors grow more sensitive, with next-generation neutrino observatories like KM3-NET and gravitational wave telescopes like LISA coming online, these puzzles will only multiply. The gamma-ray singularity isn't a solution, it's a threshold, a point where the questions become as vast as the cosmos itself. From the eerie gamma-ray fog that blankets the cosmos to the phantom filaments streaking through our galaxy, these 25 mysteries aren't just gaps in our knowledge, they're windows into the universe's most extreme and elusive processes. Each one peels back another layer of the high-energy universe, revealing the violent undercurrents shaping everything from black hole collisions to the invisible scaffolding of dark matter. The enigma of the Fermi Bubbles forces us to confront our galaxy's explosive past, while the ghostly whispers of dwarf galaxies might finally unmask the true nature of dark matter. The cosmic ray mismatch challenges our understanding of interstellar physics, and the defiant gamma rays piercing the TV horizon could rewrite the rules of light itself. Even our solar neighborhood hides surprises, with unexplained hotspots hinting at cosmic processes playing out right on our doorstep. Solving these puzzles wouldn't just fill textbooks, it could revolutionize astrophysics. Confirming dark matter annihilation in the Galactic Center would unlock the universe's missing mass. Decoding the origins of gamma-ray bursts might reveal the birth cries of the first black holes. And if primordial black holes or action-like particles explain the anomalies, we'd glimpse physics beyond the standard model. Every mystery is a thread in a grand cosmic tapestry, woven together by gravity, quantum mechanics, and the raw energy of creation. But the most thrilling part, this isn't a static story. New telescopes like the Cherenkov Telescope Array and NASA's next-generation gamma-ray observatories are poised to turn these mysteries into breakthroughs. The answers are out there, hidden in the light we're still learning to read. So tell us, which mystery captivates you the most? Is it the rogue black holes firing gamma rays into the void, the cosmic shadows hinting at hidden galactic structures, or something else entirely? Drop your thoughts in the comments below and let's keep the conversation going. The universe's greatest puzzles are waiting, and every observation, every theory brings us one step closer to unraveling them.